control. IEEE Control Society had its CDC conference, and myself, well, it's a little bit the rules of the games that you have to play, namely funding. And in Finland, things are somewhat different than they seem to be here, because I still see people working on same problems and similar problems as I used to work 25 years ago. There were some talks on power control for WCDMA. In fact, one of my good friends, Peter Keynes from McGill, had a paper, and afterwards I was trying to advise him that maybe his approach was a bit too theoretical. So might be mine. And again, I'm in very humble way coming here. But I like to give some things, some approaches that perhaps now and later will be valuable for wireless communications. What I think makes wireless communications area very fruitful area for control people also is exactly this wireless dynamic environment. It's not, we started with power control, it was sort of a natural area, but I think the larger area that one needs to look at and have contributions from control point of view is radio resource management area. So let me try to run a quick. I wanted to show you this one because I'm a control person, but I have very good friends. This is Uri Neuvo, who is the vice president in Nokia Mobile Phones, also a member of the board, we studied together in just about everywhere. He came to the States after I finished my degree, and I was already in Toronto. He finished his PhD in Cornell, and then we were in the same university, Tampere University of Technology in Finland, and about 93 or 4 he joined Nokia. My wife is saying, why didn't you join Nokia? Because in Finland you can we don't have super rich people, so that with Nokia options, Yrjö was rated in top 20 earners last year. So anyway, he is also an IEEE fellow and so on. So if I'm not that good in everything, he is. All right. The outline is should be longer, but in Europe, in Finland, we still tend to have this German type of system where you have professor, me, the guy. So let me talk about a little bit about the lab and then move on to the actual topic. We work on a number of areas. This theory part, CDC, is about theory. We don't get that much funding for theory anymore. So we have to go to industry and try to get the support, approach our national funding agency and the Trade and Industry Ministry. And in that way, most of the staff is funded. In Finland, when I went back at the end of the 70s, pulp and paper industry was the main industry, still is one of the strongest in the world. And so me, double background, control engineer, I had to learn something about pulp and paper making. But
I have the screen.
Okay.
I of course don't see it. Oh, here it is. Okay.
yes, wonderful. So we still do work in process control area, but that is not so much my area. We also work in power electronics, electric machines, but let's say that my main interest areas are wireless communications and especially microsystems, and I noticed from your staff that you also have people who have made connections with microsystems and wireless communications. So theory, well, let's say that I know a lot about adaptive, intelligent control, etc., etc. I'm not an it's infinity type of person, but I know enough methods. Here are things in process control area. I picked something from the logistic chain. Pulp and paper is something that begins from a forest, and the logistic chain has been thought out very carefully. They have very efficient machines cutting trees. There's a saw that cuts the tree, then it's put it in a horizontal position, stripped, and at the same time it's sawn into logs. And there are very interesting things which are related to that, and in near future there probably will be wireless microsensors installed, wireless communication, that's sort of simple type of straightforward idea there. Microsystems, well, we work on number of things, microassembly, biomedical applications, and here, okay, we go back to pulp and paper. Paper fibers are very small microfluidics, and this is very exciting. Communications, well, about what would I say? About 4 years ago or so, we started in earnest, and this year the first PhD thesis was finished. Since in many of the areas we are not experts, we tend to cooperate with other people, and so it is with the communications area also. We work together with our people in Institute of Digital Communications, which part of it is, for instance, communications lab, signal processing lab, and so on, have joint project with them. Finnish academies like NSF funding basic research, and we have a joint project with the other labs in our university. We have sort of, how should I say, visiting cooperation with Stanford. We have a fund still next year, and person, I think my colleagues were here, Professor Halme and Adrian Bukalov, and it's Adrian that has been especially in Stanford. We also have a joint project with KTH, Royal Institute of Technology in Stockholm, with Jens Sander, and the thesis work that was finished started in such a way that I had a grad student staying there for 1 year, and then he came back and finished his work. So we learning in a way. We are very high up in the learning curve, but it takes time, and we want to know the system. We want to know the process. We don't want to just take the data and try to apply our methods. We like to understand what's going on. So let's get back to the power control. So what you have in GSM and presumably in the first phase of UMTS in uplink power control that you have from radio network controller the zero target which you compare with the measured one, then you have the 1 bit to act as a controller. In control field this would be a relay controller, and then the here we just see a simple loop delay for the channel mobile station and channel fading interference and transmitting power is errors. So okay, in control field, the relay controller is not really the best one. It's say in air conditioning system or temperature control, one used to have a relay system. It's cheap as an actuator to implement and so on, but as far as control result is concerned, it might not be the best one. So since we in wireless communication we live in an environment that has lots of disturbances and variations, we don't know the system, the channel that well. So the issue was to us that okay, could we find a controller that would work better? So we would just concentrate on the uplink control, understanding that there are other issues involved. So when in this work we study the dynamic situation, we don't take the snapshot approach, and then of course the analysis is much harder. We have to rely on simulators, which we constantly worry about. We start with Matlab simulation. We have tried to use COSUP, and that's an endless struggle to us. Our communications lab has developed a NetSim simulator, which I will show you later what sort of things it has. And that's the sort of environment we then used once we sort of established the result. And in a way I'm not very happy about just using simulators to show that something is good. One needs more careful analysis. But of course this situation is also difficult. So in the area of control, one often faces the case when the system is unknown. In process control, many times you don't worry about modeling this system so much. You throw in a PID controller and tune it, and that's it. A bit more sophisticated approach is to use an adaptive controller, and there are many ways. Adaptive control field is a vast field. What I'm going to talk about is really self-tuning type of controller. I'm jumping back and forth, let me still go back. So a self-tuning controller can be tuned either so that you identify the system model, compute the control parameters, or you don't identify the system model, you only worry about the controller itself and use all the available measurements that you can and update control parameters. So you don't worry about this. Okay, the truth of course is not exactly so, because you need to find a structure for the controller, and there I'll give you a brief summary how, say, a minimum variance controller is derived. Some of you know this, some of you don't. So let's assume that I know the system structure, which in our case would roughly be the channel let me assume that it's a very simple one, described by yk plus 1 plus a1 yk plus a2 yk minus 1, and on this side then the input plus noise. Let's not worry about the noise. Eventually I would assume that it's white Gaussian, zero mean, and so on. So the basic problem is to minimize the variance at the next time instant k plus 1 when the history is known. Namely, I have measured all the y's and all the u's. So this is a conditional expected value. And there are two heuristic ways to derive the minimum variance controller. One is to write the system equation like this and looking for one-step predictor, or maybe you want to go two steps ahead. And here, if you want to find the best predictor, then of course you cannot do anything about future noise, so you scratch that, and therefore your best estimate would be at time k, one step ahead, this one. And if you then substitute this predictor here and do the mathematics, then this is what you get. Of course, this is a bit more sophisticated. You can make this more general. You can derive the predictor and so on. A very brief heuristic idea, the other one, is that do the same. Ignore again the noise because you cannot do anything. If you look at the cost, what you're trying to do is minimize the variance, assuming zero mean for y. So again, let's just go back here. And here is yk plus 1. So if I want to minimize the variance, then the best I can do is zero variance. Of course, there would be the noise variance, but I cannot do anything with that, so let's forget it. And it's independent assumption, assumed independent anyway. So if I want this to be zero, then choosing u in such a way that this expression is zero gives me the same answer. So this is a heuristic way, but to do this properly is that you would derive the predictor, substitute it in the conditional expected value and work it out like that. Then you get general result. But this would be the minimum variance controller structure. So now I have the control structure. Now I sort of forget the system, which has many unknown things, but I only have the structure, and control parameters would be fixed. But I like to make them adaptive, and so the implicit way is to adjust only the control parameters, and this will be scratched. So I would choose this one, and then replace y with error, where I have the measured SER and minus the SER target. Now, this sort of adaptive control goes long way back, especially to 1950s. You had the MIT type of rule for airplanes. I don't know. This was in Time magazine a few years ago. You might remember that Payne Stewart and his friends were flying, they were dead already. They were flying 2-3 hours because they had an autopilot on. Similarly, nowadays you can't go to the cockpit anymore, but a few years ago, especially with thinner people, I used to go and chat about the autopilots that they have in jumbo jets and so on. So it's a bit boring for the pilots because they have the trajectory and they set up the potentiometers and the autopilot is turned on and they have nothing to do. The plane could even land automatically. So this sort of concept works in practice very well in ships, airplanes, also in many industrial cases. Of course.
Do you remember why he died? Was there an oxygen problem?
Yes, there was an oxygen problem.
Some other control system, right? So I couldn't figure out when you put this up, was this the failure of adaptive control, or
no?
Or because the plane flew for many hours on its own?
Without adaptive control, you could have died much sooner.
Yeah.
Well, maybe the oxygen system had a control loop in it.
The story, of course, goes as far as the research in adaptive control is concerned, that like many other things in 50s, there was a lot of interest in adaptive control, and still in 60s until, I don't remember what sort of airplane, X-15 or whatever, experimental one came down, and presumably Air Force stopped funding this sort of research for a while. And then in 1970s it became a hot topic again, and now it's still active field, but since results are such that you can apply, not so much excitement there as before, except that you might go to neural networks or fuzzy and do this sort of things also there. So in a way you would then take the from the radio network controller, say target, measured zero error, and the controller would use the control history and the history of the error. And here, basically this is an estimation scheme, but you might want to make it some sort of intelligent block if you wish. But basically we are updating the control parameters based on this sort of measurements that we are getting. And okay, in more general expression would be this one, but then when we are looking at power control, we don't want to use too many terms. And then there's also one thing that you don't want to adapt too fast, so you can cope with certain changes in your system, like variations if your mobile is in the car and you're driving, then it's more efficient than if you would be stationary or you would be walking. So in practice it's also so that you don't want to update your parameters at every sampling instant, but a bit more slower. So you would use, say, recursive least squares estimation. You could use other recursive schemes. Here I presented a minimum variance control structure, but you can also have some other type of structure there. Okay. So just a little bit about the actual estimation. This structure that has two terms of the error and two meaning UK and UK minus 1, you have two B parameters, is the one that mimics then PI controller, which in a way makes sense. And so your actual model that you're looking at is this one. You can rewrite this, pick the parameters A1, A2, B0, B1, call it parameter vector, and collect your data with a minus sign, minus E, K minus E, K minus 1, UK into the data vector. Then you can write this equation in this form and apply recursive least squares algorithm, where you have the all parameter values plus correction term. This one represents the estimated error, and this is the Kalman gain, and that's computed using error covariance matrix and so on. Very well-known equations. You can the structure that I really had there is a sort of PI controller, but you could possibly think of adding more terms or looking at nonlinear terms. We tried that, but it didn't work that well. Later, when we go to the NetSim simulator, the sphere is computed with this formula that should be quite familiar to you. So okay, we have two kinds of simulation. With Matlab, we simulated just the single link, and here are some of the facts of the simulation. We approximate the zero by the received power. We had Rayleigh fading, but no slow fading. These are other things, two mobile speeds, slow, fast. And we used 1-bit command and also investigated 2-bit commands. You could have the error in these commands, so the steps that we had here was plus minus 1, here plus minus 0.5, minus 1. So this is just to indicate that we took into account these errors. And so as I said, these are simulation results, and you have to look at the results in that light. These are not conclusive results, these are indicative results. This is slow speed, high speed, and if we look at the relay, the conventional controller, and this minimum variance controller, the self-tuning controller, then we're looking at say total transmitted power. The relay controller is actually doing even better in this particular case, slow speed, but when you move to high speed, then the opposite occurs, and the numbers here tend to be lower than here. The situation with if you would be able to use 2-bit power control, then the sort of self-tuning controller would seem to have an advantage just about everywhere.
Can you go back a slide?
Sure.
I have some questions about, I guess 2 slides, to the So when you have rarely fading, you have a rarely fade value for each slot of transmission.
Yeah, so
And
it's,
it's correlated with the usual Bessel function
Yeah.
correlation.
yeah.
Given, so that all just depends on, it's characterized by the Doppler frequency from,
Yes.
alright. So that all seems alright. So essentially it's the received power of that rarely faded signal slot by slot that then your control is in response to. And the measurement you get at the receiver is
We could just go back and look here. Was it here? No.
So there was a slide where you said, oh, in fact, the experiments or the simulations essentially just use, they use received power.
That's right.
You actually recover a transmitted signal and you have to build some estimator for power.
Yeah.
Whereas-
Actually, at this point, I could go. I'll come back to this NetSim, which here NetSim it starts being a bit old simulator now, although we try to update it. But this one has tries to take everything into account in a proper way. So here we use here and not the power itself. NetSim has these main blocks, and you could say that COSAP connection would be here, and then the network simulators of NetBones would be somewhere here, and these would be in the NetSim. And so some of these things are based on measurements done in downtown Helsinki area. So this is a bit better, but still you never feel very happy about, at least in my case, that you have to trust a simulator to show that something is better than another. So the results are in a way indicative, and one can do some theoretical analysis. But at this point, let me jump into this is a sort of parallel thing. Once we got going into this direction, so one can also talk about self-tuning predictor, meaning that you would update your predictor values, and okay, this is still. Let me try to make this now quicker. So the basic issue here would be to take the received power and use the measurement history to update the predictor parameters. So you would use a predictor here to predict future values, but you would not have constant parameters. You would sort of update in the same way as I was updating the control parameters. Say you predict one step ahead. We tried 2 steps ahead, but it didn't really produce any better results. So otherwise, there's also what one calls a backup controller, where you would just use the conventional control, and there's a switch here. Otherwise, this would be about the same. Here, what do I mean by this predictor and self-tuning predictor? Well, if I have the received power description here. Let's not yet worry about what n, and in a way this could be m, what these are. So I like to develop a prediction for transmitted received power at t+1 at time t, one step ahead predictor. Prediction error is this one, and this is in a way a dual problem to this control problem. You again minimize the variance of the prediction error this time, and you can derive, this is in a general form, but okay, it's replace these with estimates, and this the updating scheme is again the same, that you would use the data history. Here the assumption has been that we have covered noise, so we don't only have these parameters but these extras. Again, recursive least squares algorithm. This one has been done only for single link Matlab, and beforehand one doesn't know for sure what the predictor structure is, but also from industrial experience one knows that it shouldn't be very high order. There are other issues like what would be the initial values, update period to get impact time, and so on. So here is actually the structure that worked nicely for slow speeds and for high speeds. Then the 3, 4, 2 referring to the fact that we have two of the former estimated received powers, and these are the measured ones. Okay. Update. Well, in a way this is a question of modeling identification, that if you have a lot of noise and you put high order model, you try to update the period very fast, and then you follow the noise rather than the actual phenomena, and so you should not update at each sampling interval. Okay, these are details. Yeah, for slow speeds, this usage is not self-evident, but like if you compare these numbers, here is the one bit relay controller, one bit prediction-based control. So again, the standard deviation of received power is actually better here, and although the total transmitted power would be less here. So for slow speeds, it's not so immediate, but when you then go to higher speeds, then the numbers here are larger than these numbers. So there is indication that this sort of predictor would be worthwhile. So let's then go to this this more realistic environment using this NetSim simulator, which has not only the power control but has admission control, has handover, and then here rate receiver and so on. So this has been an effort that has taken many years when this has been built. But as I said, it needs updating in various forms. Here we not only looked at just the power, but also probability of blocked, dropped calls, call drop probability, and here on the x-axis we have call birth rates, and here the probability the relay controller is consistently above this minimum variance controller. The reason that it saturates here is that the simulator is not able to handle any more of the mobile users in individual cells, so that actually one should not look at above that at all. So this is in fact a better way to look at the third GMV that you see here is a bit more sophisticated control structure. But so as far as core loss probability is concerned, we are consistently below.
So a number that makes more sense sort of physically to me rather than call birth rate is if you imagine you had an infinite server queue, you could say, well, what's the expected number of active calls in a cell at a time relative to, say, the processing gain, or if it's, the number of time slots, if it's time division. So for 6,000 calls per something, right? For a call holding time of 1 or 2 minutes, it comes out to, is it 20 calls? Is on average? I know that there's some. I mean, we've drawn a lot of curves just like this, but to understand sort of the physical meaning of whether your system's any good or not, right?
Well, I really appreciate this, because when we have the meetings in this project, we try to often ask that what are the sort of criteria to use.
So is this Cdma? This one is?
Yeah, this is Cdma.
So you have some processing gain. The ballpark figure that people seem to always talk about in the U.S. is if your processing gain is 100, or 100, theory says you might be able to have 30 calls active in each cell. Practice says from, maybe it's 11 to 15 and 20 if you're really pushing it. So,
well, when I get back, I will.
There is some number, and I would guess that, I would guess 6,000 is about, just as a ballpark, I guess the number active at a time per cell, I would guess that's probably 0.3 or something of the processing gain. The other thing is, what do you think is happening over here that you're flattening out and dropping calls even when the load is light?
I don't know.
It might be one possibility is that you have a sort of a policy for dropping the call that's sort of too aggressive, that doesn't reflect something going on in reality.
The insights of the simulator, we don't, of course we have studied it and tried to understand what somebody who has already left has put in, and we feel that there are things, as you are pointing out, that
But something
might be
happens.
the reason. So,
In some sense, I guess the thing is, like, we used to, a couple of years ago, we used to sort of really do a lot of this, and we sort of had a feeling that somewhere around 10 to the minus 1 is where you start losing interest. Like, if you're dropping 10% of your calls, you want you ought to run the system at lower load. And on the other hand, much below 10 to the minus 2, like people who run systems would say, there's so much sort of bad stuff happening in reality, like holes in the cell and coverage problems, that if you somehow engineer sort of an idealized model to be less than 10 to the minus 2, you're sort of wasting your time if you believe it. So it seems like the heart is between there and something over here. So in some sense, where it's flattening out there is sort of actually an important place. An operator might say it's the important place to, you think?
Probably even lower.
Huh?
I would have done it to be even lower, isn't it?
Yeah, I think if you got some combination of blocking and
Is
dropping
this packet or this is call?
below 1%, they would tell you there's enough other reasons that it's 1% that you're sort of... Anyway, it's interesting.
and here is the call blocking probability, so our understanding was that
Yeah, so that's the number, like 2% is, yeah. So between 1% and 10% is the sort of the range that operators care about.
There's not a big difference in performance, though, between those two curves.
Well, the problem is there's something funny there. It's more consistent.
It's a couple hundred calls, right? Is it 5%?
But you might say, using your
10%?
same argument, that you really don't know things that well. There are other unknowns that are probably comparable
Maybe.
to those differences.
So, it's funny, we got off track because you had that slide earlier where at some point the minimum variance control was worse than the relay control.
With the slow speeds, yeah.
And did everyone else understand why? But I didn't know why.
Well, of course, this netsim takes into account most of the things that you should take into account, and the other one was just Matlab simulator.
But sort of usually with the Matlab, usually you can at least figure out what's going on.
Well,
True, right? That's the beauty.
I probably have to press on a little bit more my students, but then on the other hand, this has been our starting point, and now we are looking at joint power control and SA smart antennas, starting to perhaps at the beginning of the year to also look at the use of location, how to combine that with the power control and maybe handover, and so as I said, this has been our window to the world of wireless communications, and I think although somewhat interesting, still there are even more interesting issues than power control. But we like to keep the power control together with the other issues. So I think this year was about, all these were some of the simulation parameters that they use in netsim. Those simulations that I showed you take a day or two to run. So as I said in the beginning, I think that control people should look more into these issues and also try to understand rather thoroughly what's going on, not only like in this case we've taken a particular control method and try to see if it produces better results. The expectation would be that yes, of course it should, but when there's dynamics involved, then I think control might have something to offer to the wireless communication area. So I think I'm going to stop right here.
I'm looking at these, and I have to say, the thing I don't see, you see, Ryan, is where the call load affects the interference. Right, so you, like, somehow you see your call dropping is going up with call load, right? So, like, I think I worked out, like, 6,000 calls per hour works out to 100 calls per minute, which is 100 over 60 calls per second. You multiply that by the call length, and you get times 180. You get 300 calls. Is the by sort of queuing theory tells you that it's 300 calls is about how many active calls you should have at a time. And somehow whether 300 calls is a heavy load or a light load should depend on what the processing gain is and how many cells you have, right? So it's like 100 calls per cell.
Yeah.
And one of those numbers has to sort of mean the...
What's the processing gain here?
I'm sorry?
You're simulating some CDMA system, right? So what is the processing gain?
See, the thing is when you go to a control theoretic single user model, right? You have to then say, oh, the interference process becomes some interference power.
What the paper lays on and Zora and I wrote, right? Basically that's what they do. You convert this multi-user problem to a single-user problem,
With
but
a
then you say
interference
the
based
effective
on the
interference
mode.
is related to all the other stuff.
But I think they're doing that because otherwise he wouldn't have dropping going up with load. So it's in there somewhere. We just haven't quite figured out where it is. It's probably on some other slides, but we're off the screen, but it's there somewhere. So is the problem you're currently working on the multiple antenna version of this problem?
Yes.
Are you focusing either on mostly downlink or mostly uplink? Do you have a thought about?
Well, we started last summer, so we have been doing the downlink. No, sorry, the uplink only, and
Are you thinking of it in the? So we did have Adrian Bukalov visit once or twice, and it seems like his interest in the Stanford project is adaptive antennas.
Yeah.
Is there a thought to combine that with adaptive antennas?
we talk with it.
Yeah, what is your thinking on adaptive antennas and CDMA, given that the mobiles will be 360 degrees? You're saying that you bring everything down to baseband. If you have N
Yeah,
antennas,
I think-
do you have N receivers then?
Well, that's an interesting point.
I mean, with CDMA, it's intuitive that you could conceivably steer an antenna per time slot. But with CDMA, it's not clear.
No, it's not.
I think it's sort of a slightly non-academic level. It's interesting how maybe funding sort of steers research. So in the U.S., we, for work that looks like something that'll help an industrial sponsor, like we can't get NSF money for this. And on the other hand, all of our industrial sponsors have been sort of in our current recession become sort of tight.
Hitting us too. right now. It's
So it seems like we mostly are able to get financial support for things that involve data, right? And for instance, one of the people who came, data is sort of the another set of issues.
It is.
That is very tricky in terms of.
But if you say I'm going to focus on the high rate data with very little processing gain and very few users, then you can maybe do some things with a smart antenna.
Yeah, right. Maybe.
Yeah, in our university we have very good people in the antenna side, and they made measurements. In fact, we visited them last week. They invested a lot over the years into the measurement system, and they have generated data.
Yeah.
They're I guess as the argument goes, that in the mobile you might have 2 and say in the laptop 4.
The thing is, it's a big problem and quite difficult. And my personal thing is I don't actually know very much about control, but I know more than the average about what the things are in the radio that you measure or you have to adjust. And Zoran knows a lot about control, and but for instance, my personal bent in this problem is that it's easy in a controlled framework to write these expressions where you say, oh, the received power is this.
Yeah.
But it's a sort of a non-trivial thing to actually measure it, and you have to average it, and the stochastic measurement is actually the characteristic will depend on what control you implement.
I agree, and in a way, from the moment that we started the cooperation, I've been a bit unhappy that usually we would go and make measurements.
Anyway, thank you very much.